we've talked a lot about Menelaus Theorem by now. So we'll move on. 4D is another theorem, a sort of cousin of this, is Menelaus Theorem. And I call it a cousin because people usually, at least I think of these two theorems as going hand in hand, Menelaus Theorem and Menelaus Theorem. As you'll see, they're sort of very similar to each other in very obvious ways. Yet despite that, despite the fact that you'll see how similar they are, Menelaus' theorem dates way back to the 1st century. When he published it in some work that he did. And since it's so ancient, we name it after him because this is the first record we can find of this theorem, but who knows if it was original to him. So that's going all the way back to the 1st century. Meanwhile, remember, Giovanni Ceva, 1600s. So quite a long time between our first references of these theorems. Well, maybe I shouldn't say first reference. Remember, we had that king of Zaragoza that apparently also proved Menelaus Theorem in the 1100s. Or was it 11th century? I think it was 11th century. Anyway, yeah, very closely related theorems, but this one much more ancient. And, yeah, let's see. So, given a triangle ABC, just as usual, let's let P, Q, and R be points on the sidelines BC, AC, and AB, respectively, and not equal to any of the vertices of the triangle. Alright, so with none of them, a vertex of the triangle. Alright, so this is what we did with Menelaus Theorem. We had a triangle and we chose 3 points on the sidelines. If we chose them to be on the actual segments, then we had interior Chevians. If we chose them to be on the extended lines, then we had exterior Chevians. And I'll just remind you, here's what Menelaus Theorem says, or rather, here's the question it answers. So the question it answers is, if I choose these 3 points, that gives me 3 Chevians. The question is, when are they concurrent or parallel? And Ceva's theorem gives us the answer, right? So, Ceva, he asks, when are the Chevians AP, BQ, and CR, when are these concurrent? And in asking that question, then you realize you have to throw in a little bit more than just concurrency. When are they concurrent or possibly parallel? And of course, we know the answer now. We've talked a lot about Menelaus Theorem, so Menelaus Theorem gives us the answer, which is if and only if an odd number of them are interior, odd number of the Chevians are interior, and the Chevian product is trivial. Right, so, and what is it? AR over RB times BP over PC times CQ over QA, if that's equal to 1. So this is even a stronger result, right? This is a if and only if statement. So they're concurrent or parallel if this is true, but also if this is true, then they're concurrent or parallel. Everyone happy so far? Right, this is just a review of what we've been doing last week. Okay, so there's in fact, more than a week. There's Menelaus Theorem. Same situation though, so we've got P, Q, and R on the sidelines. here's what Menelaus asks. So Menelaus. No longer is he looking at the Chebians, he's just looking at the 3 points themselves, and he asks, when are they collinear? When do they all live or lie on the same line? So, when are P, Q, and R, and again, the normal spelling of collinear has 2 L's in it for whatever reason, so I'll try to remember to do that. It shouldn't, but it does. So the first thing I want to look at is sort of I want to approach this the way we did with Menelaus Theorem, which is when I asked when can the 3 Chebians be concurrent, we went through all the different cases of how many are interior and exterior and odd versus an even number. Let's do that here as well. And the cases I want to look at is with how many of them live on the actual sides of the triangle versus the extended sides. So for example, the first case we'll look at is, here's case 1, 3 sides. Let me just use the number 3. 3 sides, 3 points rather. 3 points on the sides of the triangle. Is it possible if I choose all 3 to be on the actual sides of the triangle, this would correspond to interior Chebians, is it possible that they're collinear? Well, choose one. How about I choose P there? Now I come into this side, put down Q, choose anything you want for Q. How about I choose Q right there? If P, Q, and R are collinear, then R must lie somewhere on that line. Not possible, right? And not hard to convince yourself. Starting with this P, no matter what Q I chose on this side, I'm never going to get something that's collinear with a point R over here. Agreed? All right, so this is not possible. So let's keep playing this game. Let's do 1 point on the side, or sorry, 2 rather. 2 points on the side of triangle. 1 point on, now we'll extend the sides. On the extended side. So see if you can build a situation like this where they're collinear. The situation I've drawn up here is about the only way you could possibly fail, because I've chosen P and Q so that this line PQ is roughly, it looks like, parallel to this side of the triangle. As long as you choose P and Q so it's not parallel, then we can choose R so that's collinear. For example, let's choose P here and Q here. Alright, so that gives me a line. And that's going to cut through this extended side whereabouts? Right around here. So choose that to be R. Now I have 3 collinear points. Do you guys do something roughly like that? Okay, so yes, it is possible. Let's keep going. We've got 2 other cases to check. 1 point on the sides of the triangle and 2 on the extended sides, and then all 3 on the extended sides. So keep checking these, keep trying these. Do the other 2 cases. Three and 4. If you have all 3 on the extended sides, here I've just chosen P to be here and Q to be here, well then obviously this line is going to cut through this 3rd extended side, right? Eventually, I should have drawn this a little bit less parallel, but if you extend this far enough, it'll cut through right around there, so choose that to be R. That's a really terrible straight line, but... So yeah, if you choose all 3, I can't even stand this picture. Choose that to be R. P. So yeah, if you choose all 3 to be on the sidelines, then on the extended sides, then yeah, it's not hard to find three that are collinear. What about this case? What do you guys come up with? Is it possible or not? Yeah, I don't think it's too hard to convince yourself. Just start trying to draw something. What did I go with? Here's my picture. I chose 1 to be out here. Here's P. So P is on the extended side, and I chose Q to be on the actual side. Well, yeah, now you can see that sort of no matter where I choose Q on this side and where I choose P on this side, this line is always going to cut through this side line in the actual triangle itself. Right? So it's impossible to choose R lying somewhere out here, so this happens. So of course this is just one case, but I mean you go through all the cases, this is pretty clearly not possible. All right, so which cases was it possible in? It was possible when we had 0 or 2 points, 0 or 2 points lying on the actual sides of the triangle, right? And 0 or 2 points lying on the actual side of the triangle, that corresponds to, if we were thinking about Cheva's theorem, if the points lie on the sides of the triangle, those are interior Chevians. So 0 or 2 are odd numbers, or sorry, the other way around, 0 or 2 are even numbers. So this is possible when we have an even number of them on the actual sides. Sort of an even number of interior Chevians, if you want to think of it that way. So this is the complete opposite of Cheva's theorem now. This is true, or this is possible to be true, rather, when we have an even number of these points on the sides of the triangle. Doesn't mean just because you choose an even number of points to be on the sides of the triangle that it is true, but that's the only way it is possible to be true. It's sort of a necessary condition, not sufficient. But from here, I'll just tell you the theorem. This is Menelaus' theorem. And yeah, it will read very similarly to Cheva's. Given triangle ABC, let points P, Q, and R lie on sidelines BC, AC, and AB, respectively. With the one catch that they're not allowed to be vertices of the triangle. So, and assume that none of the points is a vertex of ABC. Cheva's theorem says then the three constructed Chevians, A, P, B, Q, and C, R, are concurrent if and only if something happens. Here we'll have that P, Q, and R are collinear if and only if something happens. Then P, Q, and R are collinear if and only if Cheva's is if and only if an odd number of the Chevians are interior. Here we've got the opposite, if and only if, first up, an even number of these points lie on the actual sides of the triangle, so corresponding to interior Chevians. So if and only if an even number of them lie on the actual sides of the triangle, And I'll phrase this in terms of line segments. So lie on the line segments BC, AC, and AB. But what I mean by that is on the actual sides of the triangle. And this is why I say it's such a close cousin of Cheva's theorem. Well, for one thing, sort of the things we're discussing feel very similar. But, and the Chevian product is equal to 1. So, and AR over RB times BP over PC times CQ over QA equals 1. So really nice result. Once again, we have sort of this equation, and as long as this equation is satisfied, and we satisfy this quick counting argument, then we can verify collinearity of these 3 points. Really nice that it's the same expression. And despite that, the discovery of these theorems were separated by at least 1,000 years. One thing I'll say is if you look this up somewhere else, you will almost always see this expressed as this expression equals -1. And the reason is, remember what I told you with Cheva's theorem, many people, if I put, say, P out here, if you're measuring BP over PC, as you usually would, say, this value in the Chevian product, that ratio in the Chevian product, most people use sign distances. So BP over PC to them would be negative. What happens in Cheva's theorem? Well, it doesn't really matter because if you have an odd number of interior Chevians, then that means you have think about this. Why are my signs confusing me? When is Cheva's theorem true? An odd number of interior Chevians, right?
They're saying that an even number of PQ and R are not on the extended lines, and an odd number of them are on the outside.
Yeah, so in this case, I mean, if an even number of them lie on the line segments, then an odd number outside, so you choose, say, P, Q, and R, and you compute this ratio, then you're looking at an odd number, right? It's got to be odd. So in this case, it would equal -1. But for Cheva's theorem, it should be +1. Why am I getting confused here? Oh. An odd number of interior Chevians. Yes. Here I have an even number of interior Chevians. So yeah, if you want an odd number of interior Chevians, then you better have sort of 2 of them lying somewhere outside. And if you have an odd number of interior Chevians, then you've got sort of a negative times a negative, and it'll always be positive. Again, I think I'm just losing IQ points standing at the board. But yeah, so if you look up Chaba's theorem somewhere else, again, they use sign distances, so they won't have any mention of the number of them. They will just have if and only if. For Chaba's theorem, this expression equals 1, but they're using sign distances. For Menelaus' theorem, if and only if this Chebian product equals -1. So don't be confused by that. It's a sign distance thing. And I figured at this point we probably wouldn't have time to prove it. It doesn't look like we do. So I'm going to move on to an exercise. We'll prove this at the beginning of next class. The proof, by the way, it's so closely related to Chaba's theorem, and the proof looks and feels very similar. So let's just do an example. An example of an application of this. So let's start off with a triangle. Let's go triangle A, B, C. Okay, so we've got triangle ABC. ABC is an inscribed triangle. Bit redundant there. Every triangle is inscribed, of course, right? Every triangle has a circumcircle. But here I'm drawing it as inscribed in a circumcircle. And here's P, Q, and R that I'm going to draw. P, Q, and R are, in fact, I might need a bit more space. We'll see. P, Q, and R are the intersections of the tangents at A, B, and C with the sidelines BC, AC, and AB respectively. Alright, so what I'm going to do is I'm going to draw on the tangent at A, and I'm going to look at where that intersects sideline BC. Let's see, tangent at A probably intersects sideline BC somewhere around here. And I said I was going to call that point P. We'll look at the tangent at B and ask where that intersects sideline AC. So we'll draw on this tangent at B. So it should intersect right around here. P, Q, and last but not least, tangent at C, we'll ask where that intersects sideline AB. And what's going to happen is these 3 points are going to be collinear, so I'll assume it intersects somewhere way down here. And it pretty much does. P, Q, and R. So my claim is that these 3 points are collinear. P, Q, R are collinear. In fact, they form a line that has a name. It's usually called the Lemoyne axis or the Lemoyne line. So, on a line called the Lemoyne axis or line of the triangle ABC. I really failed to keep this straight going here, but anyway. And what I want to do is prove this claim. But I'll point out that this is a specific case that I've drawn. Notice that this line doesn't always have to exist, right? P, Q, and R don't always have to be collinear. How could it fail? Well, notice that R is sort of getting pushed way out here, right? How could I make R even further away? I could have just chosen AB to be a little bit more parallel to PQ, right? In fact, I could choose AB to actually be parallel to PQ, in which case these two lines would never intersect each other. They'd intersect out in infinity. So this doesn't always have to happen, but in this case that I've drawn, it does. So we'll prove this. How are we going to prove it? We're going to use Menelaus Theorem. So I want to compute the Chevian product. I want to compute, in this case, I want to compute what are we computing? AR over RB. We want to compute BP over PC, and we want to compute CQ over QA. So our proof is we want to show that AR over RB times BP over PC times CQ over QA, we want to show that that equals 1. That's all we'll have to do, because how many of these points lie on the sides of the triangle? 0, which is an even number, right? So we're satisfied there. Okay, so let's see, proof. We're going to compute all these distances using a bunch of similar triangles. So, first, note that this angle, angle BAQ, so BAQ, this angle here, is an inscribed angle in the circumcircle. So it's equal in measure to 1/2 of this arc BC. Equal in angle measure to 1/2 of arc BC. And it's been a while since we've talked about this stuff, but if you measure the angle between a chord and a tangent, so this angle here, that's also equal to 1/2 of its sort of inscribed arc. And you can go back to that theorem for that. I think it's theorem 1.23. But you can also think about this as just sort of the limiting case of choose another point, say B prime, that's super, super close, right? And inscribe this angle. B prime to B, B prime to C. In an angle measure, that would be very, very close to arc BC. And then just push it to actually get B. And then the limit, you get arc length BC. So in any case, this angle here between this chord and this tangent is equal to, once again, the subtended arc. So that's the same as angle CBQ. What else do we have? We've got this angle here. Is angle Q, that's an angle in, and I'm just going to call this angle Q, all right? So we'll be a little bit lazy. No, maybe we won't. And angle AQB is obviously angle AQB. So that gives me two different angles that are equal in two different triangles, so they're similar. Hence, what do we have? We've got triangle QBC is similar to triangle, I want to match up this angle with this angle. It came second in QB, so this would be QAB. QAB. QAB and QBC, yes. So those two triangles are similar. Therefore, their ratio of sides are the same. So let's see, for example, QB. What does that correspond to in the other triangle? Well, you can look at this and try and figure it out. So, okay, I'm going from this angle to this angle, so over here would be this angle to this angle, so that's over QA. Or you could just look at the order they're written. QB corresponds to QA. So QB over QA. That's the same as, I want to do BC over AB last. So what's the other one we have? QC to what does QC correspond to? QB, this side matches up with this side. Again, maybe it helps to think about this visually. If I'm matching up this smaller triangle with this bigger one, what do I have to do? I have to sort of pull this vertex over here to match up with this vertex. So I'd have to flip this over and stretch it out. So anyway, this side matches up with this side in the bigger triangle. QC over QB. And last but not least, that is BC over AB. This side BC corresponds to side AB. Yes. Again, if you don't want to think about it, I find it a lot easier when we just wrote down the similarity order there, thinking about angles. If you want to just match up sides, QB matches up with QA, BC with AB, QC with QB. What is BC over AB though? BC is a side of the actual triangle, right? We usually call this side length, since it's opposite angle A, we usually denote that with little a. Right, so that's little a. And side length AB, that's opposite angle C, so that has side length little c. What do I want? If I'm computing this Chevian product, I want CQ over QA. How do I get CQ over QA from these expressions? Well, I could just multiply these two together, right? So therefore, QB over QA times, I'll keep calling it QC. QC over QB, sorry if you didn't leave space, like I didn't either. What is that? That's CQ over QA. That's exactly what we wanted, CQ over QA. Do you believe me? Is that okay? Take these two guys, multiply them together. I do get CQ over QA because these cancel. And what's that equal to? Well, they're both equal to A over C. So in products, this should be A squared over C squared. just do this again for the other two ratios now. It's pretty much the same process, so I'll just tell you what you get. So completely analogously, similarly, you can compute AR over RB is B squared over A squared, and BP over PC. Compute this, you'll find this is C squared over B squared. So now compute your Chevian product, AR over RB times BP over PC times CQ over QA. Well, that's going to be, what do we have? B squared over A squared times C squared over B squared times A squared over C squared. And I think everything cancels, equals 1. That's all we want to do, right? We have an even number, in this case 0, lie on the sides of the triangle, and the Chevian product equals 1. So by Menelaus, they're collinear. I wanted to take a moment to talk about the homework, but I also want more than 5 minutes. Do you guys want to talk about the homework? Have you looked at that? What do we have? The one I wanted to talk about was the hardest one. Showing that O and H are isogonal conjugates. So what is this? This is 4C.3. Again, I modified it slightly. It says just do it for the case where the triangle is not a right triangle. Don't worry about thinking about it the obtuse case. So just stick with an acute triangle. So acute triangle, you end up with your nice regular acute triangle here. Ooh. That's not acute. Although I can leave that point and use it again. Okay. I just wanted to draw something that didn't look like it was going to be equilateral, but anyway. ABC. And what do we have? So we've got the circumcenter of this triangle, maybe right around there. There's my circumcenter O. All right, so I don't actually use this point. And what I have is I've got the lines from A passing through the circumcenter. So I'm actually going to draw on all of them. AO, BO, and CO. And now so I don't have this too cluttered, I'm just going to come into one of these lines. By the way, these lines aren't special at all. The lines from a vertex through the circumcenter of a triangle, they're not angle bisectors, they're not medians, they're not altitudes or anything. These lines are not special, other than the fact that they happen to be concurrent. But what I'm going to do, and I think this is the easiest way to go, is this order. Start with a line passing through O, and take its isogonal. So find the isogonal Chevian. And what do you want to do? You want to show that that's a right angle. Right, if I'm trying to show that the isogonal conjugate of O is H, then all I have to do is show that all three of these line segments, AO, BO, and CO, they sort of reflect to isogonals that happen to be altitudes. So I want to show that this guy, the isogonal Chevian, which means those two angles are equal, by the way, the isogonal Chevian is an altitude. How are you going to do that? You're going to show that this is a right angle. So you'll probably want to label this point, what's your favorite letter? X. Sure. We'll call that X. I want to show that that's a right angle. Well, there's a ton of stuff we can do here, right? For example, I've already labeled this angle, and by definition of isogonal, that means that this angle over here is the same. And what you'll also want to do is go around and label all these points that I have on the circumcircle. A lot of points here, though. We've already used O, so I don't want to go M, N, O, P. Let's go P, Q, R, and S. We know how to measure angles like this, angles between two intersecting chords. Right? We know how to measure these things. For example, angle AXB. What is that? That's going to be 1/2 of the two inscribed, the two subtended arcs. That's going to be 1/2 of SC plus AB. And just by looking at this picture, you can see that lots of these arcs have the same measure, right? For example, because these two angles are the same, I know BS must be the same as PC. All right, what else can you do? You can say other things like, okay, PC. Well, these here are vertical angles, right? These are vertical angles, and this is important. This wouldn't be true at any other point, but because this is the circumcenter, and those angles are the same, well, that means that PC has the same measure as AR. So you should be able to go through and do a whole bunch of angle chasing and equating these things, and you should be able to show, with some work, that is 90 degrees. And that's the whole crux of the argument. If you can show that the isogonal Chevian for this isogonal through O is an altitude, then the isogonal conjugate of O, where this intersects, will be the intersection of the three altitudes H. By the way, you'll never be able to show alone just by doing this stuff that this equals 90, because I don't know the values of any of these things. But what you can do is you can say, well, I know this plus this. Those are supplementary, right? So if you add them together, that's 180 degrees. Is that what I want to do? Yeah. They add together to give 180, and you can show that both of those angles are the same. If they're the same and they equal 180, then individually they're 90 degrees. So proceed along those lines. By the way, the other option is start with the altitude and show that its isogonal Chevian passes through the circumcenter, but that seems a whole lot harder to me. I don't really know how you proceed there. So I think that's the hardest part of this problem, is figuring out how to get started on this, but this picture alone with these arguments should do it all for you.